unit vectors are a new quantity that will help us express vectors in a more compact way. When we're looking in the xy plane, we're introducing two unit vectors, I hat and j hat. We know that these are unit vectors because of the little hat that is on top of them rather than the little arrow that we're used to seeing for vectors. What makes a unit vector special is that it has a magnitude of 1 and no units, so it is pure direction. It doesn't contribute any numerical value or any idea of a measurement to the magnitude of the vector. All it does is have direction. The I hat vector points in the x direction, and the j hat vector points in the y direction. And so what this is doing for us is allowing us to split up the idea of a vector being magnitude in a direction into two separate pieces. We talked previously about how the components are related to the magnitude of the vector, and now the unit vectors are going to carry the direction. So we have two different parts to the vector, and we can represent that by these two different pieces. So whenever you're dealing with a unit vector, again, the important thing to remember, I hat always points in the positive x direction, j hat always points in the positive y direction. They have a magnitude of 1, and to distinguish it as a unit vector, you have to have a hat associated with it. Here we see the unit vectors along with a arbitrary vector A. We've talked about how you can take this vector A and draw a vertical line through the tip, horizontal line through the tail. You can use that to find AX and AY, the vector components. And we said that we were focusing on the X and Y components of the vector, which were the magnitudes of those vector components. But if it's a true vector component, it needs a magnitude and a direction. We were saying that we know the direction for this component would have to be in the x direction. We know the direction here has to be in the y direction. How can we show that mathematically? Well, including the I hat or the j hat vector tells us what direction it is. Again, we have the original vector, which we can break up into components. Into vector components. These vector components each have an x and a y component of the original vector. And the x component we know is in the x direction, the y component we know is in the y direction. But in practice, if you have a vector with two components, you don't know which direction each component is in, but if you include the unit vectors, now you know this has to be the x component. We know that because it's in the x direction as denoted by that I hat unit vector. We know this has to be the y component. We know that because it's with the j hat vector. So when you have numbers, you can see right away what direction these components are, which axis each one of these components is associated with. And this is a very common way to represent a vector. This is equivalent to the other way that we saw vectors being represented. This is another method here, 2, 3, with the pointy parentheses means this 2 is the x component, 3 is the y component. This is more common just because it's already kind of dealing with the math more, and we'll see how we can do more math using vector components and also with these unit vectors. Technically, there's a third dimension. In this class, we try to keep most things to 2 dimensions to make life a little bit simpler, but once you get into physics 2, there'll be a lot of 3-dimensional problems built in, and there won't be any way around it. So typically, we focus on the XY plane, but there's a Z direction, a third dimension that we ignore. Usually, the X direction is pointing out of the page at us as we're looking at the XY plane, right? This is us looking at the page. The X direction would be pointing straight out at us. And so when we do need to deal with that third dimension, we do have a third unit vector called k hat, and that points in the positive Z direction. And so in general, a 3-dimensional vector would have 3 vector components. It would have 3 numerical values, and we'd be able to tell which one is which direction it points in based on the I hat, j hat, and k hat relate to the X, Y, and Z directions. Depending on the notation in in engineering and mathematics and physics, we often use similar notation. It is seen sometimes where the I hat vector or the j hat vector or the k hat vector could be given like an x hat and a y hat and a z hat. So this would be the unit vector in the x direction. That seems a little bit simpler than remembering the I hat vector. The problem with this method and why we don't use it in this class is that sometimes you have a general vector that's some distance x in the x direction and some distance y in the y direction, and you're leaving the end of that vector as a general location so that you can maybe set up an equation that you can solve. If you instead express this as x in the x hat direction and y in the y hat direction, this can be pretty confusing because you can leave off the hat. You can forget that this is a unit vector and this is a variable, and so that can be confusing. This is more clear even if you're trying to use variable quantities there. Another thing that can be a little bit different between math and engineering and physics, this is one way that we think of writing these three axes, because we're used to having x pointing to the right and y pointing up. Another way that these axes are commonly shown are with the x-axis pointing off to the side. Kind of imagine it pointing straight out at your face, and y is going to the side and z going up. And in this case, we would usually be looking down at the page, and the x-axis would be to the right, the y-axis would be pointing up, and we would be looking along the z-axis this way. So either way, these are fine as long as the relative orientation from one to the next is the same. In fact, this is the convention that we use for the x, y, and z axes. This is a right-handed coordinate system that we'll see a little bit more when we get into the vector cross product later in this semester. You could also have the z-axis pointing the opposite way, right? You could have it like in this. This is a left-handed coordinate system. Mathematically, it would work. Mathematically, it would give you equivalent answers to what we use, but this is not the convention we use. This is the convention we use, and this is how you will always see the x, y, and z axes oriented. You'll see x pointing to the right, y pointed up, and z pointing out of the page at you. Going back to three-dimensional vectors, our vector A would have x, y, and z components that would be denoted by the I hat, j hat, and k hat unit vectors. Vector A here would be 2i plus 3j plus k. If I have just a k, there's implicit that there should be a 1 in front of it, right? That the length is 1, and then the k is the direction. So this means this would be 2 in the x direction, and then 3 in the y direction, and then 1 in the k direction, which means 1 means out of the page towards us. And so A would start at the origin and would end at the corner of this red box, 2 by 3 by 1. 2 by 3 by 1. For vector B, similar idea. We would have -4, so this is 4 to the left, 4 in the negative x direction, which is to the left, so 1, 2, 3, 4. 2 in the y direction, 1, 2 up, and then negative k means -1 in the k direction. That means 1 away from us. And then it would start at the origin and it would go to this point here. Again, we're thinking of this as a x vector component, a y vector component, and a z vector component. We typically include all three values, and we put them in I hat, j hat, k hat, x, y, and z form. But you should be careful. It is possible sometimes you might see like an I hat and jump straight to k hat. This implies that the j hat should be there, but we're omitting it because it's 0. And so what we should do in that case is go ahead and include that 0 j hat, so that way you're including all three dimensions every single time, and then you're not accidentally adding a j and a k because they're lined up, but they're using different unit vectors. You can only combine I hats with I hats, only combine j hats with j hats, only combine k hats with k hats. The vector components are all independent of one another. So an x direction doesn't see a y direction, which doesn't see a z direction. If we have a three-dimensional vector A with components ax, ay, and az, it would look something like this. Right? Again, we would have, this would be ax right here, this would be ay, and this would be az. And the magnitude of this overall vector would be the length of this vector here. And so what we can do is we can do a couple things. We can say that this distance here is going to be the square root of ax squared plus ay squared, right? This distance here is just in the xy plane, and so it's exactly the same magnitude of a vector we've seen before. This length here is the hypotenuse of a right triangle, where this is one side and this is one side, and the z direction is perpendicular. The z direction here is perpendicular to the entire xy plane. So the z direction vector is always perpendicular to this vector that falls somewhere in that xy plane. And so what we have is the side length across the bottom squared plus az squared, and we square root the whole thing. If you square a square root, those two things just cancel. And so we have a magnitude of that three-dimensional vector. We can also find the direction. To define the direction of a vector, we actually need two angles. This is another part that gets a little bit confusing. When we are measuring the angle in 2 dimensions, this means that we are in spherical coordinates. And we use a vector phi in the xy plane. That's the vector that's the angle for a 2-dimensional vector we've been using before. And then we use what's called an azimuthal angle, measuring how far we rotate down from the z-axis. So in this case, we can find this angle just the normal way. Right? We can find angle phi as the inverse tangent of the x and y components, because this angle is just a rotational angle. It's rotating about the z-axis, and so it's just going to depend on the x and y components. Right? You can imagine here we have a right triangle. This is ax along the x-axis, pointing out of the page at us. This is ay pointing along the y-axis. And so we can find this angle here from this right triangle that we have, and we can find angle phi. And that's going to give us this quantity here, which let's call AXY, because it's the component of A that's along the XY plane. If I want to find this angle here, this angle is in a different right triangle. This is the magnitude of vector A. This is the Z component of vector A. That's along this side here. And this side right here is is side length AXY. This side here is the same as that side there. And so if I want to find this angle, I have a right triangle here where my Z component is perpendicular to the XY plane. And so I can find this angle here as the inverse tangent of AXY over AZ. AXY should already be positive, and kind of in more practical terms, I can think of that as the square root of AX squared plus AY squared over AZ. We have to be, and in this case, actually, we have to be a little bit careful here. Here, we're assuming that AZ is positive. If AZ is negative,